In this video, we'll review some of the principles related to kinetics and collision theory. Let us say we take a reaction that can be described by the stoichiometric equation A reacting with B to form C. Of course, that stoichiometric equation doesn't tell us what happens in terms of the elementary steps. Let us say we do an experiment where we determine the rate law, and we find that the rate law is equal to K, the rate constant, times the concentration of A to the power of 2. We'd say the reaction is second order with respect to A and zero order with respect to B. This tells us something about how the reaction must proceed. I've written out in green a possible mechanism. It's possible in a slow step that two A molecules react to form an intermediate D, and then D goes on to react with B to ultimately form C, the product. When you add those two elementary steps, it gives you the overall balanced equation, and as mentioned, D is considered to be an intermediate. Now, collision theory tells us that in order for a reaction to occur, molecules must collide with sufficient energy and the correct orientation. So when we look at the rate law, rate is equal to K times the concentration of A to the power of 2, everything that affects the rate is built into this equation. So how concentration affects the rate is obviously connected to the concentration of A to the power of 2. How energy affects the rate of reaction and whether or not there's the correct orientation is built into the K term. Now, this K is equal to AE to the negative EA over RT is the Arrhenius equation. And the A that I've highlighted by a box in green, that's the Arrhenius factor. Now, that has to do with the chances of the correct orientation in a collision. And the more complex the molecule, the more difficult it would be for the correct orientation. The E to the negative EA over RT has to do with whether or not a particle would have sufficient energy to react. Now, the EA obviously is the activation energy. The higher the activation energy, the larger the negative exponent, and the smaller will be the rate constant. Conversely, the T component in that equation is temperature. The higher the temperature, the smaller the negative exponent, and the larger will be the rate constant. On the left-hand side, I've written two graphs, Maxwell-Boltzmann energy distributions, and let's say this represents the molecules of A in our slow step, and we're trying to see what would affect the rate of reaction in terms of changing possibly the activation energy and changing the temperature. Now, I say change the activation energy, but if the activation energy is going to be changed, it has to actually be a completely different set of steps that would involve a catalyst. So if we look at our top graph, for instance, you can see that I've shown the distribution of energy that the particles have, and those particles that are found on the right-hand side of the activation energy, in terms of their energy, those particles would have sufficient energy to react. So that would be the fraction of molecules that have sufficient energy to react. They have more energy than the activation energy. If we add a catalyst, a different pathway will be provided. So actually, there would be a different slow step that would involve the catalyst. That different slow step would have a lower activation energy. So the particles would still have the same overall average kinetic energy and distribution of kinetic energies, but the energy required for the reaction would be less. And so we could write that in here. So this would be the activation energy in the presence of a catalyst. Again, it would be a completely different pathway, so it would be a different reaction mechanism. And now you can see that there would be a larger fraction of particles that have sufficient energy to react. Therefore, the K value would be larger and the rate would be faster. So that would be one way that the rate of the reaction could be changed. Another possibility is that we maintain the exact same reaction mechanism, but rather we change the temperature. And let's say in order to speed up a reaction, we could increase the temperature. This would change the distribution of energy of the particles. So the distribution might look more like this. Now remember, the area under these curves should remain the same. I'm not sure that I've completely done that. You can see that there's now a larger fraction of particles that have an energy greater than the activation energy. Therefore, again, the reaction would be faster. In this case, the reaction pathway would be the same. It's the same activation energy. It's just that more particles have that sufficient energy in order to be able to react. Hopefully, this very quick review of kinetics and collision theory has been helpful.